Okay, here's a quick little lesson video on r squared, the coefficient of determination. We're using this formula right here to try to make sense of it. Last class, we already figured out what r was and how to get that. And it is true, you can just take r and square it and get r squared, obviously. But it's kind of a little weird because r and r squared kind of have different meanings to them. We interpret them differently. So R we just interpret as the strength of your association. Is it weak, moderate, or strong? That's really all we use it for. And of course, we know where it comes from. R squared is talking about the reduction in variation from what you started with by associating your predicted values to some x value. So let me explain. So first of all, you'll see that this is standard error on top, which is this whole big guy. Really, it looks meaner than it is. It's not so bad. It's really, E stands for all the errors. It stands for all these little errors that you get. So when you're looking at data and you're looking at a regression line, all these little errors, like that's a little error, and this would be a bigger error, and this would be a really big error. So it's basically your residuals, right? Your residuals. So we're taking all those little errors, squaring them to make them into squares, kind of like you see here. So that's what this is doing, right? It's taking each of these errors, squaring it to turn it into a square and an area, right? And then we're going to add them all up and divide by n minus 2. Now, we don't divide by n minus 1 anymore because we're talking about bivariate data. There's two variables, which introduces more error. So we have to divide by n minus 2 in order to account for that extra variation. If you think about a regression line, it has a slope and it also has a y-intercept. So both of those numbers can change, which introduces more variation. So we divide by n minus 2 instead of n minus 1 to make up for that because it's bivariate. Okay, so anyway, I mean, it's basically the standard error is just like when we do standard deviation, it's a average residual, basically, right? So we're talking about an average error. So if I look at all these little squares that were made by the data points and my regression line, all those little squares are being added up, right? And we're taking an average of all those to figure out what our standard error is. Okay, so that's that. Once you get that, you can see that that's where this comes into play. So this is like the variance of your errors, right? The variance of your errors. And then on bottom, it's kind of the variance of the variation you had to begin with. It's just the y values. So let's take a look at that. So over here, this is that roller coaster drop and miles per hour, right? Um, Before we associate the miles per hour with the drop in feet, we had variation to begin with. Maybe the average was 65 miles per hour, but we had variation, right? We had some that were faster, we had some that were slower, blah, blah, blah. But we did have kind of an average variation, right? So if I were to take, when we calculated standard deviation, we took all the little residuals from the mean up to every single little data point, every single one, and we averaged them. And we said, what's the average distance or average standard deviation away from the mean? So in this case, it looks like, if I kind of went average up, I'd be maybe here, and average down, maybe about here. Right, that's about halfway each direction. So I would imagine my standard deviation is probably like 10 or something. Okay. But now, when I come over here and I look at all these little residuals here, this little residual, right? The average is going to be much less. It's not going to be 10 anymore. This distance is going to be much smaller over here on average, right? So what we're doing is just really taking a percentage. So we're saying of this 10, and I could even write it down. Let me just estimate it. Of this 10, how much do I have left over? Well, there's some big ones here, some big squares, but there's a whole bunch of little ones too. So I think an average is going to be like, I don't know, like maybe like 3, maybe even less, maybe like 2 or something, right? Let's just say it was 2 just for the heck of it. So 2 out of 10, right? 20%. So what we're saying is that 20%, 20% of the variation I started with has been or is left over, is still remaining when I do an association with the drop in feet. So by adding this predictor onto it, I only have 20% of my variation left over. And that's what makes bivariate data, like making a prediction, um, a little better, right? If you have something that you can measure first and then use that to make a prediction, you're going to get more accurate results than if I were to just say, let me just randomly pick a miles per hour all by itself. If I just randomly picked a miles per hour, I would be all over the place. I'd have a lot more error because I could be guessing anywhere right on here, any of these things. All right, so you can see here this r squared is like 82%. So my guess of 20% was pretty good. So what r squared is telling you is what percentage has been removed. So if I have 20% left over, 20% of the variation left over, that means about 80% has been removed. It's been reduced by 80%. But we usually just say it's been removed, right? Okay, so that's really, when you look at this equation, this part of it is telling you what percentage you still have remaining. That would be like our 20%. And then when you take 1 minus that number, that's talking about how much of the variation was removed, which would be about 80% in our case. And that's really it. That's the coefficient of determination. So we would say, right, 80-20. Let me go back to my graph. I'm almost done here. So this is about 82.7%, 82.8. So I would say I have 82.7% of the variation in miles per hour of the roller coaster can be explained by the drop in feet of the roller coaster. And the reason we say can be explained by is because it's the part that's being removed. It's the part that is directly being affected by the association with the drop in feet. There's still some remaining variation, right? Maybe it's about, like, is it a wooden roller coaster? Is it a metal roller coaster? Maybe it's the temperature outside, or is it the time of year? It's cold, it's hot. Um, there's many things that could affect the speed of a roller coaster besides the drop alone, right? The drop alone is a good predictor, but there are many things that go into how fast a roller coaster is. So the drop in feet is able to reduce the variation by 82%. But there are other factors that will account for the other percentage, the extra 18% or 17% is coming from other factors. The like I said, the type of roller coaster, the type of track, the who knows what, all kinds of things probably can go into that. How good the wheels are, how lubed up they are. I don't know, right? How many people are riding it, how heavy the machinery is. All these things kind of could play a role in how fast it goes. So this remaining variation is still there because of all those other factors. 83% of your variation's been removed by the drop in feet alone. Okay.